Hi, this lecture is on the subexponential classical computation of Hafner and McCurley. It's a part of the isogeny-based cryptography summer school of Bristol 2021. The class notes are available in the comment section of this video. So, what is the overall goal of classical computation through a subexponential method? So, the first subexponential method for calculating the class group was due to Hafner and McCurley in 1989. What it states is that you can calculate the class group of an imaginary quadratic order of discriminant minus d in subexponential time L to the c, where L of d is defined by this function. What does this mean exactly in terms of orders of magnitude? So what we have is that the polynomial complexity in log delta, log d here, is asymptotically a small o of the subexponential complexity in log d, which itself is a small of exponential in log d. Now, the differences are more than just a power of each other. So, for example, if you have log d to the let's choose a power k, okay, constant power k times L to the d, that is L to the d to the 1 plus O of 1. So any logarithm, the power of a logarithmic term gets automatically absorbed in the small o here in the power of L of d. And likewise, if you have L of d to the c times d, so what we have is this becomes automatically d to the 1 plus O of 1, again, by the same argument. So what it tells us here is that those different complexity classes are so different, in fact, that every time we have multiplication by a polynomial factor, we'll always choose to ignore it in the small o of 1 in the power. Okay, so this is very convenient, in fact, when it comes to proving the runtime when dealing with subexponential runtimes. And likewise for exponential values, typically exponential values come up when we're looking at probability of success. Okay, when we want a probability of failure to be 1 over an exponential value, and we have sub-exponential powers, then we'll have very nice behavior given here. Okay, so this simplifies the proofs a lot. Now, the overview of the sub-exponential method is the following. So first, we identify our classes in the imaginary case with some binary quadratic forms. Okay, and in particular, we saw that we could generate the class group with prime ideals slash binary forms that correspond to primes for a number of these forms that is in log squared delta. Okay, and that's when we assume a generalization of the Riemann hypothesis. So for now, forgetting about the actual number of generators we want and just assuming that each of these fi's is the ith split prime, the form corresponding to the ith split prime, and we assume that there's enough to generate the class group, then we have that this following map is surjective. Okay, so what it means is that its kernel is going to give us the structure of the class group. Okay, we have this identity that Zn quotient by its kernel lambda will give us the structure of the class group, which is the output of the algorithm that we're running. So what is our strategy? First, we need to find that kernel. So in other terms, we need to find product. We want to find xi's vectors x's such that the product of the fi to the xi is the neutral elements of the class group. So we want relations between the generators of the class group. We already mentioned that during our lecture on the Cayley graph, because these are cycles in the Cayley graph. Then once we have that, of course, we need to compute this quotient, but we have polynomial time linear algebra methods for doing this, so it's really not something I'm going to elaborate too much during this lecture. So really, it's find lambda that matters. And we'll split it into three phases. First, find a lambda 0 of full rank. Then find a bigger one of small determinant, and in the end complete find the tower that ends up with lambda m being the lambda we're looking for. So the phase 1 aims to find a full rank sublattice. Okay, so the way we do this is by having relations of this form here, where basically what we're doing is we're enforcing intentionally a large power here, okay, that corresponds to the prime form of the p sub ith prime, okay, in the factor base. Now, how do we do this? We just multiply it by random products that are defined by short vectors here, until it's equal to a product of the fi's. And then once you have that, then the x that satisfies this property is just given by the difference between what you had on the left-hand side and what you had on the right-hand side, so the vector z and the vector y. Now, just a little note about this, because what we want is those vectors to be small, and this can be guaranteed by the rapid mixing properties of the class group, meaning that once you define the starting point of your random walk in the Cayley graph of the class group by the power, the 2nd power of the prime form, the ith prime form, then you know that you do not need to travel very far in order to land uniformly at random in the class group. And in particular, that means that it gives you odds of finding one of this form, one that splits as a product of the generators that you chose in your factor bases, that are essentially uniform at random, okay? So, and the vector, the length of the walk is the length of the vector y, and this also is always going to be small because these are all reduced forms and they cannot split with high powers, okay? So essentially, what we get here is a small vector, and this is made artificially large, okay? Why do we do this? Well, because we want a matrix where the diagonal elements, so the relation here, so the relation that is essentially given by the product of the fi to the a of ij, okay, which is given to us by this relation here. And what we want is it has the shape that the diagonal elements are always very large compared to the other ones, okay? So like here, like the non-diagonal element would be those little dots here, and the diagonal one is very large, always larger than the rest. And what it means, what it enforces is that the matrix cannot be, the matrix has to be non-singular, okay? So that's really a trick to produce n different relations that we know to be linearly independent because of those oversized diagonal elements which we created by forcing the starting point of each of our random walks to be a large power of the elements, the ith element of your factor base. Now the bad news is that the determinant, the only bound that we know on the determinant, is something of the form phi n to the 5n over 2 times d to the n. So something that is exponential in the values that we're considering, okay? So if you look at the log of the determinant, the log is an n to the 1 plus o of 1. So the log, the determinant has itself sub-exponential size. But we know that normally the class number from the Euler product, we expect something along the line of square root d. So the log of that, the log of the determinant that we want is essentially a log d, O of log d. Here instead we have something that's sub-exponential in log d. So we're really, really far away from what we want. Now the runtime here if we choose the right size for the factor base, so we want the factor base to be all the primes of norm L L to the 1 over square root 8 of D, and then the runtime, so if that's n, then the runtime would be L to the 3 over square root 8 plus O of 1 of D, okay? So, but then you are stuck with something that is very far away from the actual lattice of relations that you're looking for, okay? But that's a first step. It's a full rank. Now, the second step is to look at the current lattice of relations that you have and hope to hit new relations that are not contained already in lambda 0, okay? So here I've represented the lattice of relations where all the red dots are spheres that contain 1 point, okay? And I'm going to specify the radius in a second. So what we want, so this is a box that has some size 2d squared, okay? So where d is the discriminant. So we're looking at relations inside of that box. And what we want is hits outside of the current lattice of relations, because every time we do, we will decrease the index, or decrease the determinant by a factor 2. So what we can do is draw a vector at random and calculate the form that corresponds to this vector, okay? Now, that form itself does not have very good odds of being smooth. Being smooth meaning splitting as a product of the factor base element, because when it does, then you find a relation by subtracting the vectors of exponent on the left and on the right hand side. But the problem is each element, each reduced form has only so much of a probability to be smooth. So then it means you have to repeat the experiment. But rather than drawing another big vector, instead we draw now very small vectors. So we do very small random walks starting from this random vector, okay? And then we hope to find a smooth form. So to land in a point that corresponds to an element that could be written down as a product of the factor base element, the generators that we chose for the class group. Now, what it means in terms of the lattice is that we draw our f at random, okay, and we hope that it's going to be not only not hitting the lattice, but also far enough, because then we're going to do a random walk, okay, and we'll do many of them until we find a smooth form, and then it means that the relation that we find is going to be a relation that's going to be not very far away. So if that is your new lattice point, okay, so you get an x in your lattice, and you hope, so you know for sure that it will never be I should call that x prime, it will never be very far away from that x. So what you want is to draw those x's that you draw at random, you want to draw them far away from those sphere here, okay? And it turns out you can evaluate the number of those spheres from the determinant of the sublattice that you currently have. So you have a sublattice lambda 1 from sublattice of the lattice of relations, and you want to draw something far away from that lattice. So first, to guarantee those odds, you need to calculate the number of points that you have. So that's given to you by this formula. Then each of those spheres, you can bound from above the number of points, of integer points that are in those spheres, and then you can derive the probability of having this x in the box that is far away, so outside of all the spheres, okay? Now, here's the catch. Your odds are only guaranteed by the determinant of lambda 1, the sublattice of relations that you have. The more relations you find, the smaller that determinant will become, and the worse your odds will be because of being outside, of landing outside of those spheres, because those spheres are basically, there's going to be more of them, right? There's going to be new dots that are created as you get more and more vectors in this lattice, right? The lattice is going to be denser and denser, and it's going to be harder and harder to avoid those spheres when you draw your point X. So at this point, we can stop this procedure. We'll call it, say, around determinant of lambda 1 is exponential to a log to the 4 of d, okay? And that's where you can still guarantee that the odds of landing outside of those spheres are essentially, yeah, the failure probability is exponentially bad. So meaning you never fail, because if you put things at scale, those little dots are like microscopic. And then you switch to a more expensive last phase, which we're going to see here. This last phase consists in finding a tower of sublattices that will end with the lattice that we want. Now this time we draw our vectors in the box, we compute f, and then this time we hope that f is smooth. Okay, so what we hope is instead we know that each of those products is expensive to compute, and because that's the product that is dense, so it's from I equals 1 to n, so it's got n terms, okay? While previously, when you were just doing some random walks from f, you were paying the price to calculate f only once, and then many, many times, just small variations around f. Now here, we pay the price every time we test for smoothness, we pay that price, okay, of calculating the big product. So that's expensive, but the good news is, we don't need to do it too many times, because what we do with the number of relations that we perform this way, that we need to hit all the different cosets of lambda quotient by lambda 1 is given to us by Hafner-McCurley, with very, very large odds if that number is bigger than essentially a log of this quotient here, which we know here is less than log. So it's going to be less than log to the 4d. So it's a polynomial number of steps here that we're going to perform. So we pay more every time for every step, but then we reduce the number of steps. And the total runtime is this, which is guaranteed under the generalized Riemann hypothesis. So in this lecture, what we've seen is the first sub-exponential algorithm for calculating class groups. It's got lots of implications. First, that method extends to larger degree number fields, and also it unlocks other solutions to other problems, some of which we're going to see in the next lecture. Thank you for your attention.